on Geogebra, you can get loads of free resources. Maths teachers all over the world upload stuff. This is called Geogebra Tube, and I just did a search for trigonometry and pulled out some. Here's one. What this does is it shows you the graphical interpretation of all the 6 trig functions. So you should be familiar. Anyone who's not familiar with why the unit circle produces the y coordinate being sine, the x coordinate being cos, and we've got primary teachers here as well who may not be familiar. Let me just quickly show you. On a unit circle, that's the unit circle, and this is obviously how most of us introduce trigonometry beyond 90 degrees. You take a triangle within the first quadrant, so the first quadrant here, second, third and fourth, and this is a unit circle, so the hypotenuse has value 1. This is the x coordinate of this point, xy. This is the y coordinate, so that length there. So we have this angle measured anti-clockwise from the positive axis, theta. So looking at that triangle, we've got sine theta is opposite over hypotenuse, which is y over 1. So y is equal to sine theta. And cos theta is adjacent over hypotenuse, which is x over 1. So therefore, x equals cos theta. So what it means, of course, is this point here, the x coordinate at any point is cos of this angle, and the y coordinate is sine of that angle. And of course, the gradient is y over x. So the gradient m equals y over x, which is rise over run, which is sine theta over cos theta, but it's also opposite over adjacent, so it's equal to tan theta. And also, just while I'm standing with my legs apart, sine squared theta, sorry, I'm pointing the wrong thing, cos squared theta plus sine squared theta equals 1 is just Pythagoras' theorem. You can move this red point here, and you can see how sine and cos, the blue and the red, change. And the tan is a really good one, because this tan theta here, if you just think of that as, p, then tan of this angle is p over this distance, which is 1. That distance is tan theta. And I'm not going to go into why, but it's quite easy then to see why these 3 represent cot, sec, and cosec. Okay? But it's pretty cool. You can go all the way around and see how they vary. That's quite nice. And another one which is quite nice, is this one. And it's gone back. Oh no, it's there. Oh no, that's the same one. That one. I'm losing time here. Okay, so that's very similar to the one that we saw before. It shows you how the y coordinate maps out as you move around, and I get students to explain why is it that in that first bit, why doesn't it just go diagonally like a straight line? And they prove to me, which basically means they explain, that in this first bit here, it goes up very, very quickly as the angle increases. So over here, it goes up really, really quickly in that first little bit, so that by the time you get to 30 degrees, you've already gone halfway up, and then it slows down because of the arc of the circle. So that's really quite conceptual learning. What else have I got? Okay. That one there. I think this has got to be my all-time favourite. I can't stand all stations to central. I can't stand it. It's the epitome of not understanding what you're doing. And that's not to say, sorry, I'm just doing this because that lady over there can't see me. It's probably a relief for her, but anyway. So look, this is great because watch what happens. As I move that, you can see the 2 places where, on the unit circle, where sine of the angle is, in this case, 0.62 or minus 0.3. And you can see it working. And that's just such a beautiful dynamic graphic. And then you can do it for, for cosine. And you can see as you change it what happens. And you know, it's pretty obvious that cosine is going to be positive in this quadrant here and in this quadrant here, because you can see cosine is the x-coordinate and cosine is going to be negative here. You don't need all stations to central. You do the same with tan, being the gradient, is obviously positive here and here. Sorry, that's supposed to be a straight line here. And it's negative here, because the slope's negative. Cool. Right. Oh, you'll love this. So this is a sine wave. It's going through all the range of human hearing. And of course sound is a longitudinal wave, so it's caused by the particles in the air, the molecules being vibrated in this direction. Electromagnetic radiation is a transverse oscillation. I'm going to cut to a little bit nearer the end, just because I want to get through various slides. Hands up if you still hear it. Still hear it? Put your hand down when you stop hearing it. Yeah, I could have just phrased that question like, put your hand down if you're old and keep it up. Okay. So, I had a competition. We had to sing a sine wave. It's already over. Oh, come on. Sorry. What's that one there? Okay. We had to sing a sine wave. Who could sing the best sine wave? We had a competition. Okay, I'm going to try and demonstrate. Okay, I did that deliberately. This is Audacity. This is Audacity. Most language teachers know about it. It's a free resource. Most schools have it already installed. Okay, that wasn't a great attempt initially. Hopefully it got better. It's not one of my best, but... and then, okay, it sort of vaguely resembles a sine wave at this point. It's the purest of sound, a sine wave. And then as you go further along... Oh, look at that! That's pretty... I think a round of applause. And then look what happens when you get more and more harsh. You get all these overtones cropping up. I mean, that was actually just clipping because I was too loud. But look, it's the same frequency, same time period, but you can compare and you can measure it with a board ruler. Same time period, but more frequency, so you get a more complicated waveform. And that's really interesting. You can start talking about Fourier series and things. Hang on. And in fact, we talked a little bit about music and about the fact that, there's the shark again, the fact that the musical intervals are actually all precise ratios. So I didn't play that Audacity clip back, but I could have played it back at 1.5 the speed. You can do all that within Audacity, and it would sound, if you did it as 1.5, it would sound a fifth above. So I can't remember what I sang. Ooh, or something. Ooh, or something. Yeah, that's about a fifth. And these are what are called the just scales. But interestingly, in music, all of the 12 semitones have an exact ratio, which are displayed here. But in different keys, that means that you'd have to tune an instrument to the key you were playing in. And when they used to play, originally they did tune instruments for every key, and when they came up with the idea of a piano, and equal tempered scale came about, and these are the approximations to the ratio using equal temperament. And then J.S. Bach came up with this wonderful thing called the well-tempered clavier. That's the front of it. It's in German, so I won't read it out in German. And I'm going to read out something from Wikipedia here, which is obviously the font of all knowledge. The just scale, sometimes referred to as harmonic tuning or Helmholtz scale occurs naturally as a result of the overtone series. Simple systems such as vibrating strings or air columns, you could actually get a member of the class to bring in a stringed instrument and actually play harmonics on it to demonstrate. The equal tempered scale was developed for keyboard instruments such as the piano, so they could be played equally well or badly in any key. It's a compromised tuning scheme. Equal tempered system uses constant frequency multiple between the notes of a chromatic scale. Hence, playing in any key sounds equally good or bad depending on your point of view and how good your hearing is, and whether you have perfect pitch. 1722, J.S. Bach produced the well-tempered clavier, which was a composition of preludes and fugues in all 24 keys, major and minor. So that's just a little bit more information. I think I'm going to just move on from that.